So hello and welcome everyone. So in this video, I am going to discuss the solution for the question check for BST. So let's understand the problem statement and then we'll move down towards the algorithm and then the approach. So in the question, you will be given a root of the binary tree, and what you have to do, you have to check whether it is a BST or not. And it is given that we are considering that BST cannot contain duplicate nodes. So you don't have to worry about the duplicate nodes. A BST is defined as follows, and the definition of BST is the left subtree of a node contains only nodes with less than the nodes keys, right? And the right subtree of a node contains only nodes with keys greater than the nodes keys. That means for a node, all the elements which are lesser than node will be present in the left subtree, and all the nodes which are greater than that current node will be on the right subtree. Both the left and the right subtrees must also be the binary search tree. Okay, so let's understand with the help of an example. So over here I have taken the example which is given to us in the question, and this is the binary tree given to us. So what you have to do, you have to check if the given binary tree is a binary search tree or not. And we know that the condition is that left subtree contains all the nodes that are lesser than the parent node or the current node, and the right subtree will contain all the nodes which are greater than the nodes value. And over here there is no case that there would be two nodes having same value. So over here let's check if this is a completely binary search tree or not. So this is my node number 2, and on the left hand side, left subtree, I can see 1 which is lesser than 2, correct? And on the right hand side I can see 3 which is greater than 2, right? So this is perfectly fine. So the output comes out to be 1. If the given binary tree is a binary search tree, then the output is going to be 1, else the output will be printed as 0. So that was all about the question. So now let's try to understand the approach for the question, that how we can solve this question. The approach for this question revolves around a single statement that every node in a BST lies in some range. Okay, so every node, if that node is present inside a BST, it will be having some range. That if this node is at this position, then this is the range. Only this range nodes can be placed at that position. Okay, so let's take an example. I have taken one of the example of a binary tree, and now we'll be checking whether this is a BST or not. But before going that, let's see what can be the range for the left child and right child of a node. So let's say if this is my node, and the range of this node is from A to B. Okay, and so what will be the condition over here? I'm not including A and B. So let's say A and B are not included. The range of this node is from A to B. So its left child will be having the range that is from A to node, because we know that all the nodes on the left hand side are going to be lesser than the nodes value. And for this, all the nodes for the right subtree, it is going to be greater than the nodes value. So I need the minimum value to be node, and it should be whatever is the upper range for the node, right? So it will be having range from node to B. So now let's try to find the range of every node in this binary tree. Okay, so we know that root does not have any parent, right? So its range will be from minus infinite to infinite. So now let's move in the left subtree 4. So now let's see what can be its range. Over here, the boundaries will not be included. Okay, so I'm keeping the round brackets. So now for this, the range will be from, what will be the range? You can observe A to node. A is what? Over here, this is A, this is B. It will be from minus infinite to 8, because all the values should be lesser than 8, right? So now let's say if I'm moving to this 6. So over here you can observe the range will be from 4, because all the nodes should be greater than 4, right? 4 to, and the upper range will remain as it is. And for this node number 2, the range will be, it should be lesser than 4, right? So the upper range will be 4 and the lower range remains as it is. So its range will be from minus infinite to 4. So now let's see what will be the range for 13. It is present on the right subtree of 8. So it should have all the values greater than 8, but it should be lesser than the value B. Right? Now let's see for 17. It should be greater than 13 and it should be lesser than infinite, right? And for 9, it should be lesser than 13 and the minimum value remains as it is. As 9 is the part of the right subtree, it should be greater than 8 and it should be lesser than 13, right? So this is the range for every node inside this binary search tree. So now in order to check whether the binary tree is a BST or not, what you can do, you can simply check the range of each and every node in the binary tree, and if that node is falling in that range, then you can say that the given binary tree is a binary search tree. So these are the ranges. Range of a node will be from A to B. Then the range of its left child is from A to node, and the range of its right child is from node to B. Okay, so now let's try to figure out what can be the algorithm. I have written down the algorithm, so let's check the algorithm. So here is the algorithm for checking whether the binary tree is a BST or not. Okay, so I have taken one of the recursive function I need to do a simple traversal on the given binary tree. That's why I've taken a recursive function, and you can traverse the binary tree in a very good manner using the recursive function, right? So over here, this function has 3 arguments. One of them is the root node, other is the low, and other is the high. These are the range, low to high. Now, if the node is null, I'll be returning true, and the return type of this function is going to be true or false. It will return a Boolean value. If the entire binary tree is a BST, it will return true, else it will return false. If the node is null, then that means it is a binary search tree, so you can return true. Now, if you encounter a node which is not in this range, low to high, then that means from that point itself you can conclude that the entire binary tree is not a BST. So that means if the node's value is lesser than low, or if the node's value is greater than high, then at that point you can return false. Else what you can do, you can traverse the left subtree and then the right subtree. So I'll be making a function call on the left subtree, and the low value remains as it is, and the high value will be changed to node's data. And now I'll be making a call to the right subtree. So I'll be doing node.write, and the low value will be node.data, node's value will be the low value, and the high value remains as it is. So this is how you can check whether the binary tree is a BST or not. So now let's talk about the time and space complexity, right? So over here, what do you think will be the time and space complexity? If we observe carefully, do you see any kind of node being traversed again and again? No, I cannot see. So over here, you are traversing the entire binary tree only once. So let's say if you are given a binary tree that contains n number of nodes, right? So what will be the time complexity? So the time complexity will be order of n. And what about the space complexity? Have I used anything extra? No, I haven't used anything extra to store the answer, right? So over here, there would be space occupied by recursion. Hence, the space complexity will be equivalent to what? So the space complexity will be equivalent to the height of the binary tree. Because let's say if you are given a skewed binary tree and there are n number of nodes, right? So how many times do you think recursion function call will be made? So n number of times, right? Because this is a skewed binary tree. Hence, the size of that recursion stack will be order of n. So the space complexity comes out to be height of the binary tree, or you can say order of n. So I'm writing down height. So this is the time and space complexity for the approach which we saw right now. So now let's try to see the implementation part for the same. So over here, I have written down the code in Java, but the same can be implemented with other languages as well with the help of the algorithm, right? So here is our function is BST, okay, and the argument passed to this function is a root node, and the return type of this is BST is Boolean. So what I have done, I have made a utility function, and that goes by the name fun, and the first argument is root node, and the other argument are the range of that node, low to high. So initially I have passed the root node, and the low has been passed as the minus infinite, and the high has been passed as positive infinite, right? So now this function, here is our base condition. If the root is null, then I will be returning true. And if the node does not lie in the range low to high, then that means from that point itself, you can conclude it is not a binary search tree. So I'll be returning false. And now over here, I'll be making a function call to the left subtree and then a function call to the right subtree. Both this function call will be returning a Boolean value, either true or false, right? And now if you observe over here, both the left and right subtree must also be binary search tree. So keeping this in mind, I have used logical AND. That means both the left and the right subtree should return true. Neither of them should return false. And then from here, the value will be returned to the parent function calling. And then at the end from here, this function will return the final declaration for the binary tree, whether it is a BST or not. So now let's try to compile and run. And we can see that the compilation has been successfully completed. So now let's try to submit the solution. And the problem has been successfully submitted. I hope you understood the editorial part. So this was the solution and the logical part for the question check for BST. Thank you.